on the cloth.
All right.
Hello, everyone. Thank you for joining, and thank you for the invitation. I think it's a great idea to hold such a seminar. My plan is to give a very clear talk, and please ask any question you have. I don't have a very specific goal. I want you to understand some ideas, but please stop me many times. And you can also ask questions in the chat. I will try to look at it through the talk. So I want to talk about a discussion that I had for some time with Olivier, Steve, Shai, and Ramon. And this is about some phenomenon in learning, in statistical learning. So first I want to explain the background for our discussion and explain in a very high level what were our reasons to think about it. Then I will formally define the notions I want to consider, and the definitions will be written, but something that is not trivial is to understand the definitions. So please ask me questions about them if you have them. And then I will tell you what is the theorem, the phenomenon, and a little bit about the proof. So this is the plan. Okay. So the background for this work, for this discussion, starts with learning theory, which is it can be interpreted in many ways, but for me it is how can you use mathematics to explain some things that happen in machine learning, which is very successful today. But the main thing is mathematics in the theory part for this talk. So we want to build a mathematical model that will help us to understand some property of reality, of this success of machine learning. And the standard definition of learning is PAC learning, probably approximately correct learning, which was very, very influential. It started this whole machine learning phenomenon. And the reason we wanted to think about it is that this definition, although it is very, very important and basic, sometimes this definition does not capture things we care about. So we want the definitions we work with to be as accurate as possible, to capture the most information as possible about what we try to model. The specific thing we wanted to change the definition, to make the definition more informative, is regarding the rates, the learning rates. So the topic I want to explain is what is a learning rate and what are their properties. And the reason is that it is a more accurate definition, more informative definition than the standard definition. So this is the very high level picture I want to explain. Okay. So now I will start by building the framework a little by little. So the framework is the mathematics. So the framework of learning in general is we get some data, and we want to use this data in some way, in some useful way, to predict things in the future. The way we model it mathematically is we have a sequence of n pairs, x1, y1 up to xn, yn. This is the input data we get. This is the observations we see in the world. And you can think about it, x, let's say, is a picture and an image, and y is, does the picture contain a dog or not? So something like this. So this is the data we have. Now we want to take this data and translate it to a useful object. What is the useful object in this formalism? It's a function. So can you see this? Maybe this is a better color. It's a function. So we want to take this data, this tuple of endpoints, and transform it into a function. This function will try to explain the data in the best way possible. This is what we sort of try to do. And we call the way we translate the input sample to a function the learning algorithm. So we call it an algorithm, although it has nothing to do with an algorithm. It's just some function. There is no computability anywhere here, okay? So this is the framework. We get S, we want to output from S a function H, and the way we do this computation, we call it the learning algorithm. So this is the framework, and now I want to explain what do we want this algorithm to satisfy. So the high level, or the high level.
Sorry to interrupt, can I ask a question?
Sure.
Yeah, so do you mind going back one slide? So just to make sure, so here, what is X again?
X is some set, let's say R, the real numbers, or a finite set, or some abstract set.
See, so it's just an index in here, or okay.
Yeah, so you can think about it in real life as the collection of images, or something like this.
Okay, thank you.
Okay. And so the property we want the algorithm to satisfy, it is called generalization. It is something like this. We want the property that if this S, this input data, arrives from some distribution mu in an independent way, so we get n independent samples from some distribution mu, then we want the output function, the output we compute on this data, to somehow be close to this distribution. This is still not a definition, just some intuition, okay? And the way we measure this distance, this closeness, is like this. We sample a pair from this distribution, and then we check how often H agrees with the output Y. Okay, so this is the way we measure the success of our algorithm. This is the error parameter. Okay, so the distribution plays two roles here. One is the distribution generates the data. Two, the distribution allows us to measure distances. And this is the maybe most important, the two roles the distribution plays is one of the things that make this PAC learning definition so important. Okay, and now when we try to make this into a formal definition, there is some barrier we need to overcome, one more idea we need to introduce, and this is the idea of a context. So intuitively, if there is no context, then we cannot perform learning. for example, if we look on this sequence, 1, 2, 3, 4, 5, the next element is 6, only because we have some context in our mind. So yeah, this is just intuition. There are a few ways to make this idea of a context into a definition. And the one specific way, which is the way we will choose today, is that we will have some collection of functions, H. So this is a collection of functions. And we will require the input distribution to come from this class of function in the following sense. The infimum of the error rate for all functions in H is 0. So you can think about this infimum as a minimum if you want. This is not very important for this talk. Okay, so we think about that, we assume the distribution mu that is generating the input comes from some class of function H. This is how the distribution looks like. Okay, and this is a way to formalize the notion of a context. We know where mu came from. Okay. So with this in mind, we can finally define PAC learning. So here is the definition. This is not the standard way this is defined, but there are less quantifiers, so I prefer this definition here. So first, the error parameter of an algorithm with context H and sample size n, when the algorithm takes n samples, is the following thing. We take the hardest distribution, it's the supremum over all distributions in this context, and then we measure the expected error of the algorithm. Okay, so we take the hardest distribution, and for this hardest distribution, we measure the expected error the algorithm made. This is, if this number is small, this means that no matter what the distribution is, the algorithm produces a reasonable hypothesis output. And PAC learnability means, so a class of function H is learnable if there is some algorithm that makes this error parameter go to 0 as more samples are seen. This is the definition of learnability. Okay. And so there are many. There are many layers of definitions here, but this is maybe the most central definition in learning theory. Okay, and this definition is not only interesting conceptually. There is also a very fundamental theorem about this definition. A theorem that was proved by these people says that a class of function is PAC learnable. This is equivalent to some combinatorial property of H. So the property is that the VC dimension of H is finite. I will not define it here because I think it's enough definitions, but the point I want to make is that this very abstract definition that deals with probability distributions is equivalent to a very combinatorial property, a very simple, relatively simple combinatorial property. So this is sort of a bridge between combinatorics and computer science. So this is sometimes called the fundamental theorem of statistical learning theory. And now what I want to try to explain is what is the problem with this? What is this missing? What do we want to know more? Okay. So the starting point of what we want to know more or one of the places it appeared is a paper by Schumann. So this will be, again, a high-level slide. The idea is that if we actually look on a learning, we look in reality, what happens in learning, when more and more samples are gathered, the error, our performance is getting better and better. The error goes down. And the way the error goes down is important. It's either, it can be useful to predict the way the error will go down in applications. And it will actually be also useful if we can estimate this plot as we go along in the real world. So this was Schumann's idea, that the way the error tends to zero is important. And the problem with the VC, with the PAC learnability, with the VC theory, is that the way the definition there works, the distribution mu is chosen after we choose the sample size. After we choose how many samples we get, somebody else chooses the hard distribution for us. And this is not what happens in real life. In real life, there is some distribution, we don't control it, and then we can choose the number of samples as we go along. So sort of there is this switch of quantifiers. So the way we capture this in a definition is we measure the rate of the algorithm A. It's a specific algorithm with respect to a specific distribution. It is the way the error tends to zero as a function of the sample size. So this is now this graph I plotted before. And this is for a specific algorithm and for a specific distribution. And now we just increase the number of samples. Okay, so this is the rate of an algorithm for a specific distribution. Now, this is a schematic picture of how does the rates for some specific class of functions look like. So every distribution has its own rate. You see, all these lines are some distributions, and every distribution has its own rate. The theorem we saw above tells us that the upper envelope of this picture, this line, is something like the VC dimension over the number of samples. This is what the previous theorem tells us. I didn't state it like this, but this is the content. You can prove this more accurate statement. But when you run experiments and you fix a distribution, then you focus on a specific line, and in experiments, the rate is not 1 over n, it is much faster, it is exponential in n, it goes to 0 much, much faster. So now we wanted the theory to fill this gap between this theorem and what at least these people saw in experiments. Okay, is it okay?
So Amir, can I interrupt for a moment and ask you to
Sure.
define VC dimension, if you're not going to do it at some point?
I'm not going to do it.
Or at least explain it in some informal way, because this is I see many people here from algebraic combinatorics where this is not a standard notion. Thanks.
So I will define a similar notion in a bit, and I hope I can then address the VC dimension as well. But the reason I'm not doing it, I think it is not very important. You can think about it as being some constant this is like 10 if you want. This is not crucial for understanding the picture I'm trying to portray. Okay, so now we can we want to make this this gap into a definition, into mathematics. So the way we define, there is this, again, this class of functions, so which is the context of the problem. But now we want to define the rate of this class of functions, how hard it is to learn this class of functions. So the rate is at most R. R is some function that tends to 0. So R is something like this. And if there is some learning algorithm that produces error that tends to 0 like R, but there is, for every single input distribution, a different rate, some delay factor. If mu is hard, then this constant is 100. If mu is easy, this constant is 1. So it always goes to 0 in rate R, but up to some rescaling of time. So this is the rate at most R, and rate at least R means the opposite. I will, so you can think about it as being the opposite of this, not being smaller than R. Okay, so now we have a definition for some learning context R. We can ask, what is the rate? How hard it is to learn in this context? So a few comments about this definition. In the way the quantifiers are set, the algorithm does not know the distribution. So the algorithm still does not know the distribution, as in the standard PAC learning definition. This is one comment. A second comment is that not all distributions are equivalent, are as easy. There is this delay factor. This delay factor captures how difficult is the distribution. The larger this constant, the harder this distribution. So these are two comments. So we gave a definition of a rate, and now the theorem, which is a trichotomy, is that this rate can be exactly one of 3 functions. There is no other options. Either it goes to 0 exponentially. The next option is that it goes to 0 linearly. And the next option that it can go to 0 as slow as one wishes. So this is it. There is no other option. And this holds in the realizable case, in the context we defined previously. And these definitions are just, I write them, but they are not important at all. You can, yeah, this is really not important, and this is measurability. I will not talk a lot today. So, okay, so this is the statement. These rates can either be exponential or 1 over n, or as slow as we want. So it can either go to 0 like exponential. The next option is 1 over n, and the next is basically as slow as you want. Yes? Okay. So some comments about this is, the first comment is that, for example, this rate is not an option from this is what the theorem says. Just as an example. Another comment is that Schumann's proved a similar statement for a very specific case, which is, he proved the dichotomy for specific case, which is chains. I will not explain this, but the thing I want to explain, and it will be related to something like VC dimension, is that intuitively, the more complex H is, the slower the rate should be. It is harder to learn in a more complex context. And the way the complexity of H is characterized here is by the type of devices it can shatter. So this is a combinatorial property. And this is sort of a more informative information than VC dimension. And I will try to explain it now. Okay, so here is one part of the argument. This part says that the rate is exponential, which is the first case, the fastest rate possible. This is equivalent to the fact that this class of function h we look at does not shatter an infinite little stone tree. What does this mean? So a little stone tree is a binary tree like this, and the inner nodes, all of these nodes, are labeled by points in the set X. And every such tree, every node in such a tree defines a partial function. Yeah, this function, for example, maps x1 to 1 and x3 to 0. So this node corresponds to a partial function. This class of functions, H, shatters this tree if for every single node in the tree, there is a function in H that reaches it. Okay, this is the meaning of shattering. For every point in the tree, there is a function that reaches this point. So if there is an infinite tree that H shatters, the rate is 1 over n. And if there is no such tree that H shatters, the rate is e to the minus n. This is the content of what the proof tells us. Is it okay? Okay. I want to tell you two ideas, or I hope it will be clear. So I will not explain the full proof, but there are two ideas I want to convey. So one is, the statement I just said, I will focus on the upper bound. If H does not shatter an infinite tree, which is what we saw above, then the rate is exponential. This is what we want to prove. So, and here the definition of exponential rate is written. And this is a very maybe confused. How do you prove such a thing? So the thing you want to prove is that the fact that there is no tree gives you an algorithm. This is a sort of a strange conclusion. And the way it is done, which is happens in many cases, you can take the non-existence of something and deduce the existence of something else. And this is done via duality. Duality is a general mechanism that tells you there is no something, then there is something else. So I will give you one example, which is well known from geometry. So the simplest example is that if two convex sets are disjoint, there is no point in the intersection, then there is a separating hyperplane. This is duality. So no point in the intersection, then there exists something. And another place where duality appears is in game theory. If one of the players does not have a strategy, the other player does have a strategy. So again, duality. And in our context, this duality is indeed in a game theoretic duality for a class of games called Gale-Stewart games. This is set theoretic games. And a real problem we face after we notice this duality is that this duality tells us that there is some strategy, but this strategy is very, very abstract. It comes from set theory. How can we control this duality, this strategy? Eventually, we care about probability distributions. So for example, is the strategy this very abstract mechanism produces, is this strategy measurable? It was not obvious to us, the reason that it is measurable. And the way we eventually proved it is using, again, set theory. So I will try to be very brief about this, but I hope it will give you one idea. So again, now I'm trying to explain how do you prove that this very abstract strategy is measurable. It is not crazy. So the first idea is that if you have a game, it is very natural to associate to a position in the game a value. The value is how many steps you need in order to reach victory. This is a value for a position. And if you have access to this data, maybe you want to move to the position with smallest value. This will guarantee a win as fast as possible. And in an infinite game, in a set theoretic game, this value is an ordinal. Okay, so this is a standard way to define values. And in our context, you can define an ordinal. There is a natural way to define the ordinal. I will not read it even. And once you understand that this definition is an ordinal and it makes sense always, then you can use results in set theory to prove that this ordinal, this is some ordinal, it's not crazy, it is countable. You never reach uncountable sets as long as this class of function is reasonable. So, and this is a very general definition. Okay, so the conclusion here is that this very abstract set theory can actually come back to prove that something makes sense, that some strategy is measurable, which is was very surprising to me that the whole thing we were able to compile it. Okay, so this is it. So I will just summarize and then I'll be happy to answer more questions. So the summary is that the way we define learning rate, it captures some more data, some more information because it is for a specific distribution. And the theorem tells us that there are exactly 3 possible learning rates in the realizable case, in the way we defined context. And the way this is proved, it has 2 parts. The rate is characterized by a combinatorial structure, by a shattering capability. If there is a shattering, meaning there is, for example, there is a tree, then you can build a hard distribution, a distribution with not so small rate by force. You look on this tree and you build a distribution. This is one direction. If there is no shattering, then you get an algorithm, and this is done by duality, by game theory. And the way you control this algorithm is again by set theory. When you look on, for example, the ordinals that sort of come with this strategy. Okay, so this was my talk, and I'm over time. So if you have questions, I will be happy to answer.
Thank you.